Hello, class. You're going to learn about capacitance today. A simple definition of a capacitor is two parallel plates with a certain area separated by some distance, d. On these two plates, you can charge them by conduction, one positive and the other negative, so that you have one plate with high potential and the other plate with low potential. Therefore, between these two plates, there is a potential difference, aka voltage. One of these plates are charged. They stay charged until something discharges it, like connecting a light bulb between the two plates. The capacitor is not like a battery, where the light will stay on forever or until the battery dies. It actually loses charge over time and the light will dim. In between the capacitor, you can put different insulators, also known as dielectrics, in the middle to help increase the capacitance. For right now, we'll leave the dielectric as air in between the plates. The picture to your right shows what a capacitor looks like as electronics. Here's a circuit diagram showing V for voltage. That's right, I said V, not VBA for voltage. Now, starting at this point in the chapter and in the following chapter, we're going to switch from VBA to V for voltage. In this diagram, a battery is used to supply the voltage. Q stands for charge. This plate is positive and the other is negative. The variable C is going to stand for capacitance. Now, it's important not to confuse the unit for charge, which is C for coulombs, and the variable for capacitance, which is also C. In a circuit diagram, a long line next to a short line represents voltage, and two equal parallel lines represents capacitance. We'll deal with circuit diagrams more in the following chapters. Here's the equation for capacitance, where Q equals CV. The charge build up on the plate is proportional to the capacitance and voltage. The value of capacitance actually depends on the geometry of the electrical component. So with given capacitance, as the charge on the plate increases, so does the voltage. The unit for capacitance is farad, and we'll use the letter capital F. Mr. Farad is equal to Mr. Coulombs over Mr. Volts. Here's the equation for actually calculating the capacitance, which depends on the geometry of the electronic piece. Epsilon naught is a constant number of 8.85 times 10 to the negative 12. And A stands for the area of the plate. D stands for the distance between the two parallel plates. Dielectrics are insulators in between plates, and we would multiply this equation by dielectric constant, technically it's kappa or K, which depends on the type of material. Like for air or vacuum, the dielectric constant is close to 1. But for any other type of dielectrics, the constants are listed in the table. Dielectrics are useful for storing more charges on the plate. We'll take a closer look at this in a later example. Here's our first example, and we'll start off with air in the gap. We want to calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters and are separated by a distance of 1 millimeter air gap. To calculate the capacitance, we'll use this equation. But notice that our problem doesn't give us area directly. So we must calculate the area of the rectangular plates. Now it's important to do unit conversions correctly into meters. If you multiply in centimeters first, then you must make sure your unit conversion is squared. Now it's just a plug and chug. But notice that I converted millimeters into meters. And we get a capacitance value of 5.3 times 10 to the negative 11 farad. Or I can just say 53 picofarad. Here's a conceptual example about dielectrics. An air-filled capacitor consisting of two parallel plates are separated by distance d and is connected to a battery of a constant voltage V and acquires a charge Q. While it is still connected to the battery, a slab of dielectric material with K equal 3 is inserted between the plates of the capacitor. Will Q increase, decrease, or stay the same? To explore this question, let's examine the two equations related to capacitance. If K increases, then the value of capacitance also increases. But the voltage always remains 12 volts because it's connected to a battery of 12 volts. So mathematically, according to the top equation, Q will increase. So the higher the dielectric constant value, the more charge the capacitance can store.